All right. Well, welcome everyone. I'm very pleased to start the introduction of Marilena Loverde, who will be giving our colloquium today. Marilena, who just joined our faculty last autumn. She is the inaugural holder of the Dr. Ann Nelson Endowed Professorship. And this new professorship received a tremendous outpouring of support from a great many donors who wanted to ensure that we honored and continued Ann's legacy here at the UW. And the endowment in Ann's honor is still growing, but to date, just about $1.2 million have been committed from over 120 family, friends, colleagues, including many here in this room, many people listening on Zoom. I also want to acknowledge the support of the Heising-Simons Foundation and the Sloan Foundation, both of whom also stepped forward to honor Ann's legacy in a significant fashion. So I thank everybody who contributed to the Ann Nelson Professorship. It was a great help in our successful recruitment of Marilena away from Stony Brook. And with that, I'm going to turn things over to Jason to finish the introduction.
Okay, thank you, Larry. It's my honor to introduce Marilena Loverde. Marilena did her undergraduate studies in math and physics at Berkeley, and she did her PhD work with Lam Hui at Columbia. She graduated in 2009 with a thesis from 10 to the minus 35 seconds to 13 gigayears studying structure in the universe. She then held postdoctoral positions at the Institute for Advanced Study in Princeton, and then at the Kavli Institute for Cosmological Physics in Chicago, before becoming faculty at Stony Brook in 2015. And as Larry mentioned, just last year, she joined us here at the University of Washington as our first Dr. Ann Nelson Endowed Professor. Marilena's research interests are in theoretical astrophysics and cosmology, with a focus on astrophysical probes of fundamental physics, the formation and evolution of large-scale structure, cosmic inflation, the cosmological imprint of neutrinos, dark matter, and dark energy, and other physics. She's one of the elite members of the Science Council of the Cosmic Microwave Background Stage 4 experiment, and she also co-chairs 2 of the working groups on that collaboration. She's also an LSST Dark Energy Science Collaboration member, and in 2017, she was awarded a DOE Early Career Award for this work, and she's hosted or coordinated numerous conferences on these topics. We've invited Marilena to deliver our first Ann Nelson Professor Lecture, which honors the memory of our brilliant and beloved colleague, Ann Nelson, and the physics that she loved and contributed to so deeply. And today, Marilena will tell us about From Planck to Hubble, the universe as a laboratory for physics across 30 orders of magnitude. With that, I'll hand it over to you, Marilena. Thanks.
Thank you. It's a tremendous honor to have received this professorship, and I'm thrilled to be here at the University of Washington and at the physics department in particular, and join the really exciting research program that's happening here. Dr. Nelson's impact on the field was enormous, and I didn't have the opportunity to know her personally, but her legacy is great, and to have received an award in her name is really a deep honor. So thank you. Today, I'm going to tell you about a research program in cosmology that covers the range of physics over an enormous number of orders of magnitude. My goal in this talk is to tell you about 3 topics which I find particularly exciting in the field of cosmology right now. And I added this emphasis because this is a field that still continues to develop and has lots of prospects for discovery. So I am optimistic that there may be surprises beyond this. But today I'm going to tell you about 3 topics that I'm excited about. One is prospects for discovering new particles. with cosmological data sets. 2 is trying to ask questions about the origin of the universe and the explanation for the initial conditions of our universe, and prospects for connecting that to questions in quantum gravity. And finally, I'll briefly discuss the mystery of the accelerated expansion of the universe today. I realize I'm spanning more than 30 orders of magnitude here. How is it that I hope to discuss this enormous range of scales? So the study of our universe encompasses an enormous range of scales for reasons that I will convey, but including studies of physics at the smallest scales that we sort of dare to imagine and talk about, which is the Planck scale, all the way up to the largest observable scales, which is the size of our universe and the Hubble scale. So I'm going to begin with talking about prospects for discovering new particles. I'll spend the most part of my talk on this topic because it's going to allow me to give an introduction to Big Bang cosmology and how we are able to learn some things about the universe at extraordinarily far away locations in the universe, spatially, and at times which are much earlier than our time today. The first fact that we need to start with is the fact that the universe is expanding. This is something that was theorized and discovered in the 1920s following Einstein's publication of his theory of general relativity. So I want to spend a moment to talk about what that means. Here's a cartoon patch of the universe with pictures of real galaxies measured by the Hubble telescope pasted on here. And the fact that the universe expands means that the typical distance between these galaxies, or the physical distances between these galaxies, is growing with time. The galaxies themselves are not expanding because there's enough matter inside of them to hold all of the stuff together and resist the background expansion of the universe. So the expansion of the universe is not relevant to us within the galaxies, but what is increasing is the typical distances between objects. And a way that we would measure that, for instance, is by sending light signals from one place in the universe to another place. And we would find that the time it takes light to leave one galaxy and reach another is increasing with time. And that's one way that we can measure that the physical distance, the physical separation is growing. Now, along with the separation between galaxies growing, the separation between little peaks in a light wave is also growing. So that is light and photons traveling through the universe are stretched along with space. So light is stretching, and as light stretches, it cools. So the universe is expanding, the distances between things are increasing, which means that the amount of stuff in the universe is diluting. So matter dilutes and the universe gets less dense with time. This is another cartoon illustrating what it means for space to be expanding. And these little boxes illustrate some region of the universe with stuff moving around. And what changes as the universe expands is the distance between things increases, which is very visible. So the amount of stuff dilutes. The light that's traveling through the universe redshifts and becomes cooler, having longer and longer wavelengths. But the momenta of all of the different particles that are in the universe is also decreasing. So stuff that is moving with respect to the cosmic grid will be slowed down by the expansion of space. And so in the same way that the wavelength of light is stretched as the universe expands, making the energy of light decrease, the momenta of everything else in the universe is also decreasing along with the expansion of space. So this means that as time passes, oops, this has died. The universe becomes less dense and it also becomes cooler and stuff slows down. So the matter cools and dilutes. And the converse of this is that in the past, the universe was hotter and denser. And so if we want to study the universe at earlier times, then we need to know how matter behaves at higher temperatures and higher densities. Conversely, if we can learn the history of the universe or learn about different epochs in the past, then we can learn things about how matter behaves at high temperatures and densities, and therefore use the universe as a laboratory to study very high energy physics. So that's going to be the theme of my talk and how we are able to use this physics to learn about the universe in the past. So let me give a diagram of some of the scales that we might be talking about. This plot shows the temperature of the universe measured in giga electron volts are these units here. Today, the typical temperature of the universe is about 3 Kelvin or 10 to the minus 4 EV. As I go back in time to earlier epochs, the physical separation between things is smaller, and I can compute how much hotter the universe was at early times. And it grows, the temperature of the universe grows almost linearly with the size, the inverse size of the universe going towards the past. So when objects were about 100 times closer together, the temperature of the universe was 10 to the minus 2 EV. When objects were about 10 million times closer together, the typical temperature in the universe was comparable to that in the sun, and so on. So as we go further and back in time, things become hotter and hotter and hotter. And eventually we approach temperatures that correspond to energies that we study in particle colliders here on Earth, but even expect to go beyond that to some higher temperature where we don't know what the absolute maximum is up here, but we do anticipate that things continue to increase, get hotter and hotter as they go to the past. For reference, the density increases, the energy density of the universe increases much faster. So today, if I just took a 1 meter chunk of a random location in the universe, the average density would be about 10 GeV per meter cubed. So that's about 10 protons per meter. As I go back in the past, the energy density increases, and it increases quite dramatically because the amount of stuff in any given volume is increasing, but the temperature of that stuff is also increasing even faster. And so going to epochs earlier in the history of the universe, we approach times when the energy density of the universe becomes reaches things that are comparable to stuff on Earth, and then becomes dramatically higher. And so making a timeline here showing typical size of the universe, typical temperatures, and typical densities, we can ask about how what types of things we would expect to happen in the past based on how we know matter behaves at different temperatures and different densities. So going towards the past, one of the first big phase changes in the type of matter that's around is that when the temperature of the universe is about 1/10 of an electron volt, the typical energy of photons is sufficient to ionize hydrogen. So prior to this temperature, or when the universe was younger than this distance measured, when everything was 1,000 times closer than it is today, one no longer had neutral hydrogen, but instead had ionized hydrogen, free electrons and free protons traveling around. The time of this transition was when the universe was about 400,000 years old. Stepping back further, one approaches a time when helium goes from being neutral to being singly ionized at earlier times. And at even higher temperatures, but all in the sort of same ballpark, one doubly ionizes hydrogen, and so just has, helium, and just has helium nuclei and free electrons scattering around. Continuing this game of asking how matter behaves when it gets hotter and hotter, one finds that there is a time before which one wouldn't have atomic nuclei. So instead of having just protons, along with helium nuclei, deuterium, trace amounts of lithium, one would just have a gas of free protons and neutrons. This transition happens over a period of time when the universe ages from seconds to minutes, and temperatures are of order 100 keV. Now, one thing I want to point out is this is a very young universe compared to today. The universe is about 10 billion years old, but the physics that we need to describe these epochs that I've given so far is very well understood physics. We understand atomic physics, we understand nuclear physics sufficiently well to do these calculations. So while it might sound very grand to try to study the universe when it is seconds old, this is something that we can achieve with physics that is not speculative, but something things that are have been known for some time. At sufficiently high temperatures, the typical energy of photons is sufficient to pair produce electron-positron pairs. And so at sufficiently early times in the universe, in addition to all the regular electrons, protons, photons that I've been discussing, there would be positrons in thermal equilibrium along with electrons. At similar times, the temperatures and densities are sufficiently high that neutrinos are in thermal equilibrium with all the stuff in the standard model. So today, when the universe is cooler and less dense, cosmic neutrinos travel mostly like little ghost particles traveling freely through everything without interacting much. But at sufficient temperatures and densities, they collide just as strongly as, just as frequently as all of these other particles, which interact more strongly. Coming to earlier times, one finds a point where you would know at sufficiently high temperatures and densities where one would no longer have protons and neutrons, but would have free quarks and gluons persisting. Now, the question one wants to ask is, what else could there be? So I've described some physics, which is relatively well understood, and these processes that we hope to learn, that we have learned some things about going back in time, but might hope to learn more about. But there may be other particles. So suppose there are other new particles in our universe. It's a bit, I mean, one would only have to presume that there probably is some other new stuff that's around that we have not yet discovered on Earth. And if that other new stuff interacts with our standard model particles, there is likely some time in the past when temperatures and densities were sufficiently high that other stuff would have been in thermal equilibrium with all the stuff in the standard model. So one thing we hope to do is to ask, suppose there are other particles that do interact with our standard model periodic table of elements type stuff. If those particles did, then at super high temperatures and densities, those things would be produced and be in thermal equilibrium with everything else. At some point, the universe expands and cools, and these new particles would decouple from their interactions, but they may still be around today. And if so, we can hope to detect and infer their presence. One example of something like that is particle dark matter. So we believe that a good fraction of the energy of the universe is in some mysterious, unknown, possibly heavy particle, which we call dark matter. If that dark matter was thermally produced, that means that there's some time in the early universe when it's hot enough and dense enough when these dark matter particles could be produced in collisions with other types of particles. At some point, the universe cools, dark matter no longer scatters, the abundance of those particles freezes out, we say, but this stuff remains a big part of the backbone of the universe today. Yes?
You said that the dark matter would be heavy particles.
It could be, yeah.
So why heavy and not extremely light?
Well, if it's thermally... Yeah, if it's thermally produced, then it should be heavy so that its velocity is. Oh, sorry. To repeat the question for people on Zoom, it was why did I say dark matter? Well, it could be heavy, it could be a light particle, but the answer is it has to be cold. So I'm not going to talk much about dark matter, but in order to solve, I'll talk a little bit about it. We know that dark matter must be non-relativistic today, and have been non-relativistic for much of the history of the universe. So either it has to have a very low temperature if it's light, in which case it probably wasn't produced in this mechanism, or it was produced thermally and is heavy. Yeah. Exactly. So because the statement was, aren't neutrinos an example of the opposite of that? So they decouple while they're relativistic. They have very small masses and they cannot be dark matter because they're moving too fast and their velocities kinematically forbid them from clumping up to make the structure that we see today. And so dark matter has to be something that's cold enough that it's easily gravitationally bound. Thank you for the question. Okay, so how can we detect particles which were produced in the hot Big Bang? a variety of ways, but one way is we can use the cosmic microwave background radiation. So the cosmic microwave background radiation is the light, the majority of the photons in our universe, and the most abundant known particle in the universe, there's like 400 of these per cubic centimeter, are photons which were produced in the early universe, continued to scatter for long periods of time off of everything. And then when the universe cooled sufficiently to form neutral hydrogen, the universe rapidly transitioned from being opaque to being transparent to light. And the light that was emitted at this time, it's the oldest light in the universe, was produced very early on, travels through this very dilute universe around us today, and we can measure it with satellites or ground-based experiments. And we can learn a lot from it. So the first thing that we learned when it was first detected in the 60s is that this cosmic microwave background photons, the radiation that we receive is isotropic. So this is supposed to be an all-sky map showing that the temperature of this light is the same in all directions. If you make a histogram of the amount of photons, depending on their energy, you find that the cosmic microwave background spectrum follows a perfect black body with a temperature of about 3 Kelvin or 10⁻⁴ eV. This black body is measured so well you cannot see the error bars on here. And in fact, one of the experimentalists who worked on this Kobe Firaz project that measured this told me that this is like, we know that the temperature of the cosmic microwave background agrees with the true emission spectrum of a black body better than we know the actual theory curve for what a black body should look like. So if you take the Planck distribution, you get a very simple prediction for the for this curve. And that has been verified experimentally, but not as accurately as the fact that what they do with these experiments is they put antennas out. My crude theorist understanding, they put antennas out in the sky, and then they compare the difference in temperature between what they see in the sky and some perfect thermal emitter. And that difference is smaller than the known accuracy of this black body curve, which is cool. So this is spectacularly well measured. There should be some deviations from this. So this light is the thermal background light, but these processes of hydrogen forming, hydrogen and helium recombination happening will emit photons at the recombination line energies that don't have time to thermalize. So there actually will be tiny deviations out in this tail of hydrogen and helium recombination lines. No experiments have been sensitive enough to detect those. And in fact, people haven't tried that hard to design experiments that are, but it's an interesting thing that could happen in the future. There are some other predicted deviations that there should be a tiny chemical potential in the standard cosmology that is also well below the detection threshold. This measurement of the spectrum has actually not been updated since the early 90s with this experiment. But from this, we learn about the early universe. We learn some things about time-dependent processes in the early universe that allow us to limit injections of energy at different epochs. But we actually can learn a lot more by studying not just the overall properties of that radiation, but by making maps of a spatial map of the cosmic microwave background. So I'm going to spend a few minutes talking about how we do this. So what I previously showed was that big green blob, which is meant to illustrate that the temperature of the cosmic microwave background is extraordinarily uniform. If I look for deviations from uniformity, that is, I look in different directions and measure the temperature, I'll find very small fluctuations. These fluctuations are of order 1 part in 10,000. So this is an all-sky map from the Planck satellite showing variations in the temperature in different directions on the sky. A lot of exciting new information is coming from experiments that are getting better at not just measuring the temperature, but measuring fluctuations in the polarization of this microwave background light. And that's what's shown in this map. And these are harder to measure because they're smaller. These maps are from the Planck satellite, which was a European satellite mission, but this is an ongoing active area of research. And so I just want to highlight some of the things that are happening. There are a number of ground-based experiments, current ones, the South Pole Telescope, Atacama Cosmology Telescope, that are making much higher resolution maps of the sky in temperature and in particular polarization. There are other measurements that are making low resolution, but very, very, very sensitive maps of the cosmic microwave background. And these have a difference. The science goals of these high resolution ones are slightly different than the science goals of the low resolution, very sensitive ones, but they're all making these baby pictures of the universe to increasing precision. There's a super experiment, which I've been quite involved in, which is the CMB Stage 4 experiment, which unites some of these teams that have been working in different locations on the globe to make an experiment which has one set of telescopes at the South Pole that makes very, very, very deep maps of the universe, and another set of telescopes in the Atacama Desert in Chile that makes very, very, very high resolution maps of the universe at these early times. And we'll hope to get, I'll highlight later some of the exciting things that we hope to learn from this. Okay, so how can we use these maps to learn stuff about the universe at earlier times? So I've changed the way I'm showing the cosmic microwave background. I was previously showing a projection of a map of the sky onto the plane, just like we project the globe onto a map. And now I'm showing the cosmic microwave background as a sphere. Because what I want to highlight is that this is a map of the universe at a particular time. And that time is the instant when all of those photons were released. So the universe was opaque and busy. And then everywhere, all around the same time, the photons were free to just travel. So the ones that we see today are all emitted at a fixed time early on in the universe. And therefore, we see them all coming from a fixed distance from us, which is the distance photons could have traveled between the time they were emitted and the point that they reach us. So that map should really be represented as a sphere. This is a map of the universe on a sphere, some great distance from us today. Yeah.
Why the shape change from an ellipsoid to a sphere? One slide to another. This is not there.
Oh, I'm sorry. So the question was, why did the shape change from ellipsoid to a sphere? I meant to explain that, but I probably didn't go there. So just like we make maps of the Earth as a globe, and we make maps of the Earth that look like ellipsoids like that, where we project it. That's what these maps. These are all sky maps projected onto a flat 2D surface. But the map is truly a sphere. I'm sorry? Yeah, that's right. So the question was, if the light has been traveling for some time, it could have undergone. The question was, if the light has been traveling for some time, it could have undergone some scattering. And indeed, that is something that one looks for. And we find that some small percent, like 6 or 7% of the photons have scattered between that time and today. And so in fact, modern cosmic microwave background experiments learn a lot about the universe at the time the light was emitted, but also gain lots of information by learning about propagation effects, which include both scattering off of gas along the line of sight and gravitational lensing. Okay. Now, we don't stare at these maps to analyze the data. We stare at this. Yeah. Sure. Oh, I think I don't know how to make it stick better. Is that okay? Okay. Let me know if it drops again, because I don't always notice. Okay, so this is a map of very, very, very small fluctuations in something. And we have observed that this map, the statistical properties of this map are very accurately characterized by that of a Gaussian random field. And that means that the power spectrum contains all of the information that we need to predict these maps, not the particular realization, not whether it's hot here and cold here, but what is the typical size of the what is the typical amplitude of these hot spots, and how large are they physically? So we want to study things like, what is the physical extent of fluctuations, how large are the spots on the sphere, but also how bright are they, how hot and how cold are they. And that information is contained in this power spectrum, which is essentially the variance of the temperature fluctuations. And we plot it as a function of multipole moment L. So we do a spherical harmonic decomposition of this and then plot the power spectrum here. This means that the small scales are shown on the right and large scales are shown on the left. Now, it turns out that if one is studying this system, these fluctuations are small and linear and Gaussian. And that means that each mode, meaning the size of spots the amplitude of temperature fluctuations, delta T over T, at a given physical scale or multipole moment L, is independent of the amplitude of temperature fluctuations at a different multipole moment. So I can consider the evolution of these guys, and that's separate from the ones of these guys. And the dynamics of this is such that how hot or cold the universe is at a physical scale depends mostly on what the universe is doing at this combination of things, which includes the expansion rate of the universe at some earlier time and the distance to the cosmic microwave background. So we measure the cosmic microwave background on a sphere, which is some large distance away from us. And for each hot and cold spot of a given angular size or multipole moment, that hot and cold spot is telling us about the universe at a range of times, but primarily at the one that corresponds to this, the time when the expansion rate of the universe was this value, h. Yes?
The question is, does this give the distribution of matter at that time?
Yes, yes. The question, this map tells us where things were hot and cold at that time, and that corresponds to where there was excess matter, where there was more matter and less matter. Okay, so let's unpack this a little bit. So for each physical scale, we learn about the universe at a specific time. What time? The time when this was when the expansion rate was given by this factor. This means that that each physical scale here corresponds to measuring properties of the universe at different epochs. So different physical scales, meaning different L's, map to studying the universe at different times or different expansion factors. This means that small scales probe the universe at earlier epochs and large scales probe the universe at later epochs. So features in this power spectrum, which have been gained from that map, tell us about what the universe is doing at different times and what types of matter are present at different epochs. So let me give a few examples. The most striking feature in this is that there's these series of wiggles here, and the wiggles start at this scale. To the right, everything is wiggling, and to the left, things are not wiggling. They are just flat. So this means to the right, the photons in the universe are oscillating at earlier times, and to the left, the photons in the universe are not oscillating. This transition corresponds to the time at which photons are scattering frequently off of electrons and protons, we call baryons in cosmology, and that whole system is oscillating together. If I have a collection of photons that are scattering a lot off of other things and I hit it, that system will oscillate. If you do the same thing at a later time when photons are not scattering off things, they won't oscillate. So this peak marks that transition. Similarly, another feature that is visible here is an overall damping of this series of things. And this has to do with the fact that these things at earlier times, these higher scale modes, experienced a lot more scattering off of electrons. And so the temperature fluctuations get washed out the longer the scattering persists. So this overall damping scale tells us something about the number of scatters, the typical number of scatters that photons have undergone in the early universe times their mean free path. And this tells us in turn about the age of the universe at that time. Finally, a very subtle feature, which is just barely visible on this map and really only visible on the theory curve, but better detected through other means, is this slight upturn at the bottom of this curve right here. So things look flatter and then turn up slightly here. And that transition marks the point when the universe, the energy budget of the universe is goes from being dominated by non-relativistic matter to being dominated by dark energy and having accelerated expansion. Okay, so using this data, you can do things like measure the energy density in different types of particles. These are all gravitational measurements, so we can't actually measure things about the charges or certain other properties of these particles, but you can measure how they behave under the force of gravity, and that allows us to group them into things like non-relativistic particles and relativistic particles. The non-relativistic particles we know include protons and neutrons, atomic nuclei. We have also identified a new contribution to the non-relativistic energy budget, which is definitely not stuff from the periodic table of elements. And it has been named dark matter. So there's some other non-relativistic stuff that's around that's not what we know and love and detect on Earth. On the other side, on the relativistic side, we know that light and photons are relativistic particles, and we measure lots of them. We also expect that there are contributions to the relativistic energy budget of the early universe from neutrinos with very small masses that are so hot their masses are irrelevant at that time. So one thing we can do is use these measurements of the energy of different types of particles and ask if there are other additional contributions to the energy of the universe that have not yet been identified so far. So one of them is dark matter, and we need to learn more about it. But on the other side, we may expect that there could be other new particles which are relativistic in the early universe that perhaps have something to do with dark matter or some other exciting beyond the standard model physics. So if we're just studying the things, if we don't expect anything new, then one would expect that at the times probed by the cosmic microwave background, the relativistic energy density in the universe is just comprised of photons and neutrinos. And from these relatively simple physics arguments, there's a firm prediction for the energy density in neutrinos for each neutrino state. And that is that neutrinos are a little cooler than photons because some processes have not heated them, and they have a slightly lower energy because they're fermions. One would also expect at the times probed by the cosmic microwave background that the neutrinos have stopped scattering frequently off things, that the universe was sufficiently dilute and cool that neutrinos just propagate freely. This in turn means that studying perturbations in the amount of neutrinos spatially, that they should behave differently than perturbations in the photons, which are scattering frequently. And the specific quantity that is distinct between these two cases is one quantity anyways, is the propagation speed of perturbations. So if I have a excess amount of radiation in photons, that stuff is scattering frequently, and that behaves like a perfect relativistic fluid with a sound speed that's a little smaller than the speed of light. If I have a blob of neutrinos that are not scattering off anything, but just moving at the speed of light, that blob will just propagate at the speed of light as well. And so we can ask the data three things. We can ask two things. We can ask the data, what's the energy density in relativistic particles? Is it what we expect from neutrinos? Because we can measure the photon energy density directly today. And are the neutrinos behaving like the free streaming particles that we expect? Or are they behaving more like radiation that is coupled to itself? And this is something that I've studied recently. And in fact, cosmic microwave background allows two scenarios for neutrinos. So this plot is a diagram showing the constraints on the energy density and radiation, which is measured in terms of what we expect the neutrino energy density to be, and the time at which that radiation decoupled. So there's two blobs, which are the two regions that the cosmic microwave background data allows. There's one blob up here, which has which is a region in the parameter space allowed by the data where there is the expected number of neutrinos, meaning 3 neutrino species as predicted by the standard model, and they decouple at some early time. We only get a lower bound on the decoupling time because we're not able to probe early enough eras with the CMB. But in this case, neutrinos are allowed to interact until the universe was 50 years old. Standard model neutrinos should have stopped interacting at 1 second, but that's okay. We can't see back to 1 second yet with this particular data. So this is the normal standard model blob. But interestingly, the data also allows this region over here, which is completely different. The data allows neutrinos to have slightly lower energy density than we would expect. So they're a little bit cooler, where there are fewer of them. And they continue to scatter off each other and interact until the universe is 4,000 years old, which is way too late and would mean they're interacting way, way too strongly. So this mode is actually totally incompatible with particle physics, but it's allowed just by the current cosmology data. And I show this to give an example of the types of tests that we can do. It is exciting to continue looking for additional new particles and asking whether they self-interact. And this is some ongoing research, and there is no evidence for any new particles that self-interact, but there is room for them to exist, and one could hope to jointly study this with current and future data. Now, one thing that I find particularly exciting is that about cosmic microwave background experiments, and in particular the CMB stage 4 one, is that we are entering an era where these experiments can probe increasingly tiny additional contributions to the relativistic energy density in the universe. So let me explain that on this plot. So there's an interesting fact that if we know that there was some light particle that was in equilibrium with the standard model, and we know when it ceased to be in equilibrium with the standard model, so at what time it decoupled from its interactions, or what the temperature of the universe was, then one can make a firm prediction for its contribution to the energy budget. So there's a lot of stuff on this, but let's focus on this. Suppose we had a Weyl fermion or a Vector particle. These are particles with different spin that was ever in thermal equilibrium with the standard model at super, super high temperatures. So beyond at or beyond what we can hope to probe in colliders. There is a threshold value that stuff will, if we know it was in equilibrium, then it must contribute a little bit to the energy budget today. And it contributes about a few percent of the energy that a single neutrino predicts, that a single neutrino contributes. So as these cosmic microwave background experiments put stronger and stronger constraints on the energy of stuff in the early universe, we are on the contribution to the energy density of this stuff, we are probing the universe at higher and higher temperatures. Our current experimental constraints are around here, but the next generation of experimental constraints are going to make this giant jump from looking at probing the universe, things that were in equilibrium below the QCD phase transition, to going well above the QCD phase transition and starting to reach temperatures at which all other particles in the standard model were in equilibrium. Okay. There are also lots of other exciting things that we hope to do with these experiments, in particular study neutrino mass. We hope to get a 3 to 5 sigma detection of even the smallest allowed neutrino mass. There are other novel signatures of neutrino mass that you can probe. One of my graduate students, Sharuhas, has thought about some aspects of this. I'm not going to talk about it, I just want to mention it. And my grad student, Kaio, is thinking about other novel effects of having massive neutrinos present in our universe that we might use to hope to identify specific neutrino-y signatures of these particles. Okay. The CMB experiments, unfortunately, if one wanted to detect, what I've shown is that from cosmic microwave background, you can limit the time that neutrinos interacted, the decoupling epoch for neutrinos, to being about 50 years, or on the years time scale. But standard model neutrinos decouple at times of like 1 second. So if I wanted to see standard model neutrino decoupling, I'd need an incredibly high resolution CMB experiment to probe super small scales. But unfortunately, those scales would be totally overwhelmed by astrophysical foregrounds. So I just want to mention a complementary way of looking at neutrino interactions that's ongoing work with my postdoc here, Zach Weiner. And this is a test of neutrino interactions via gravitational waves. So neutrinos present in the universe, if they are scattering or if they are free streaming, will affect the propagation of very long wavelength gravitational waves differently. So specifically, if I have some primordial background of gravitational waves, then that the amplitude of those gravitational waves will be damped, and they will be damped more if a lot of neutrinos are, if most of the radiation in the universe is free streaming like neutrinos. If everything is scattering, the gravitational waves are, well, they're damped, but not as much. If most of the radiation is free streaming, then the amplitude of these gravitational waves gets damped increasingly strongly. So let me show you what this would look like if one was able to measure primordial gravitational waves across a huge range of scales. So this is a plot that was made by Zach, and it shows the energy density in gravitational waves on this axis as a function of their wavelength. So small scales probe earlier times, which are illustrated here up on the top with this temperature axis. So small scales probe the universe at early times when it's hotter, and large scales probe the universe at late times when it's cooler. The epoch of neutrino decoupling would be visible in the change in this gravitational wave signal that occurs right here. This feature would correspond to standard model neutrino decoupling. And if I allowed neutrinos to decouple later and later compared to what I would expect, then the shape of this gravitational wave signal would go later and later. So unfortunately, there is no planned experiment that hopes to reach this level. So one needs a much better gravitational wave experiment. And more importantly, we definitely need there to be primordial gravitational waves in order to discover this effect. But I think it's some really nice work that's been done by Zach here. Okay. In the last 10 minutes, I'm going to talk about these two other topics which are exciting that connect to questions one might have here. So I showed this timeline of universe expanding and cooling and diluting, but one wonders how far back this goes, how small or how close together was everything, how hot was everything, and what got it started. What made the universe so hot? Why is the cosmic microwave background so smooth? Why are the differences in the temperature of these cosmic microwave background photons 1 part in 10,000 when they come from places so far away? They never would have had the chance to. When these photons are coming from places that would never have had the chance to be in causal contact or be in equilibrium. Why is the universe so old? Why didn't it just form and was so inhomogeneous that it just little patches just recollapsed right away? And where did all this structure come from? Not only is the universe smooth, but there is this beautiful pattern of structure in the cosmic microwave background radiation and the distribution of galaxies at late times today. And we have a theory that dynamically connects all of those things and explains it. And it is the following. It's called cosmic inflation. And this theory is that prior to the hot Big Bang, so prior to this phase of hot Big Bang particles, everything is scattering off each other in thermal equilibrium, there was an epoch where the universe expanded, and it expanded enormously. That expansion took a tiny region of space, which could have been in causal contact, and stretched it to an enormous size, which encompasses the entire observed universe and beyond, so that everything that we see today, even things that look like they're very far apart and never could have communicated, were once in a very, very small region and had the opportunity to equilibrate and look similar. So this is the theory of cosmic inflation. And this process makes the universe very, very smooth, and it makes it spatially flat so that it can grow old without recollapsing in a big crunch. It also generates all the structure that we know of through quantum fluctuations during this period. Okay. When this period of inflation ends, there's some enormous amount of energy that's driving it, and that energy is dumped into particles that then create the hot Big Bang. After that time, the universe expands and cools, and then this connects back on to the rest of our thermal timeline. So this is some epoch that we're adding at the beginning of the timeline prior to all this other stuff to explain the initial conditions. If one studies this, one finds that quantum mechanical fluctuations at this time are important. So rather than inflation taking place, this exponential accelerated expansion taking place in the same way everywhere, there are small variations in how inflation is occurring at different patches in the universe. And those small variations are caused by quantum fluctuations at that time. These quantum fluctuations will cause some patches of the universe to stop inflating and begin the hot Big Bang earlier than other patches. The regions of the universe that stop inflating, begin the hot Big Bang, have more time to expand and cool than regions that ended this period of inflation later. So the quantum mechanical fluctuations in this epoch cause variations in how much inflation has occurred in different places, and variations in how much time different patches of the universe have had to expand and cool. So when viewed from afar, where we can see all of these different regions at a fixed time, this appears to give small variations in the density of the universe from place to place. And this gives a prediction, this theory gives a firm prediction, relatively firm prediction, for what the initial conditions of the universe would look like. This is possibly one of my favorite ideas in science, that we really truly think that the reason our galaxy exists is that there was a quantum mechanical fluctuation long ago that resulted in this little patch of the universe being a little bit more dense than another region that doesn't have a galaxy. So we truly think that this is where all the structure in the universe came from. This theory is phenomenally successful at giving a dynamical explanation that connects the smoothness and flatness of the universe and the statistical properties of this map. So by statistical properties, I mean specifically the correlation functions, that they are Gaussian, and things like the typical amplitude of hot and cold spots as a function of size. Our universe appears to have started with just as many very large hot spots as very small hot spots. And that's something that connects specifically to the flatness, the smoothness and flatness of the universe. On the other hand, this theory has some serious, raises questions. So the theory works very well from a bottom-up perspective, where we just invoke this period of accelerated expansion, say it happened, then we can calculate these quantum fluctuations, we calculate structure, it works really, really well. If you try to ask whether you can build a microphysical model of inflation, you run into a little bit of trouble. You tend to require that the stuff that's driving inflation has a potential energy, which has a peculiar feature, which it is super, super flat for a very long time, and then changes to allow inflation to end. This is a little bit suspicious because this long, flat stretch is a surprise from a perspective from a more microphysical model building perspective, where one might expect that if one was going to study some degree of freedom like the inflaton over very, very, very large ranges in field space, that there would be structure in this potential, that one would not be able to get something that was so flat and so smooth for so long. Moreover, if we detect primordial gravitational waves from inflation, or one just invokes some of the original models that were written down, these we need this long flat part of the potential to occur over many, many Planck masses. So we need to have a potential that is controlled over many M Planck, which is particularly surprising. And some string theorists will tell you you can't do it. Some will not. Another surprise from this is that these quantum fluctuations, which gave structure, if we detect gravitational waves, or we have some of these original models of inflation, then some of the quantum fluctuations, which eventually were stretched to very, very large scales and became classical, actually started at scales that were smaller than the Planck length. That may or may not bother you, but it definitely tells you that, well, it doesn't definitely, it may or may not bother you, and there are ways around it, but it is certainly the case that trying to create a microphysical model of inflation is in principle an opportunity to probe quantum gravity. Examples that people have come up with where they can try to create a microphysical model from string theory or something often include predictions for other observables that we might measure and learn about. And this is something that we hope to have major increases in our understanding of from experiments searching for primordial gravitational waves and experiments searching for primordial non-Gaussianity. And my student Charuhas here is also working on that. I'm just going to spend 1 minute, maybe two, talking about the mystery of today's accelerated expansion, which is my third puzzle and sort of most spectacular failure of possibly of using theoretical physics to predict some things that we observe. Okay. From a variety of astronomical measurements, we're able to map out the expansion history of the universe. This is not, there's no data here. This is just a curve with a theory that fits our data really well. And here's what the expansion of the universe looks like. The amount by which things are stretching is growing with time, with a power law for a long time. And that power law changes a little bit over the history of the universe, but the universe continues to expand. The expansion is decelerating and it's growing at a power law rate until, bam, relatively recently, the expansion of the universe switched to accelerating and growing exponentially. Now, this is a puzzle. Why is this happening and why did it happen today? Even before this discovery, this was a puzzle. You can actually accommodate this. One can actually accommodate this by making a really small modification to Einstein's theory of gravity, general relativity. One can add a constant term to that theory where there's some new constant lambda, which is some new constant of nature. And the value of that constant of nature, what is it? It's the one that gives us accelerated expansion today. And this works. But it's a puzzle because it's not what one might have expected. Even before the discovery of the accelerated expansion, there was a little bit of a puzzle, and that one might have expected that there was accelerated expansion that began not today, not a million years ago or a billion years ago, but when the universe was very, very, very young. That in fact, at super early times, the expansion of the universe was accelerating. And then we would have never formed any structure. Nothing would have ever, we wouldn't have had any chances for us to exist. So for us to exist today and to see the expansion of the universe that we see today, the accelerated expansion of the universe that we see today, you need a peculiar fine tuning, which is that the vacuum energy, the thing that can cause this accelerated expansion, has to be, the value of this constant has to be almost precisely cancel the predicted value of the vacuum energy, but not cancel exactly. So before the discovery of the accelerated expansion, people assumed that there was never going to be accelerated expansion. And for some reason, these two quantities were exactly equal. Then in the late 90s, it was discovered that the expansion of the universe is accelerating. And now we find this peculiar cancellation where these two quantities almost cancel, but not precisely. And it's a puzzle. It's a real puzzle as to why this happened. So what is ongoing work now to try to test this? Because this is an explanation. This is a model for why the expansion of the universe is accelerating. Change Einstein's equations. But it's not the only way to get the universe, the expansion of the universe to accelerate today. And so one wants to check whether the rate of acceleration is constant in time and constant in space. And many experiments are doing that. And so one hopes in this decade to begin to see some interesting progress, at least looking for deviations for this cosmological constant. And my personal bet is that we spend 10 years trying to find a deviation. And if we don't, people will probably work on something else and assume that the cosmological constant is there, at which point theory is probably going to guide us as to why this has happened, we hope. But I don't know. So today I think this is a great puzzle. If I think about it too much, I can't sleep. And I really don't know whether, I personally don't know whether data or theory is going to lead us to the answer of that. And this is a picture. If you Google theoretical physics, Natalie Paquette comes up as the fourth image. So that's why this is Natalie Paquette, who joined the physics department just last year. Okay, thank you. In conclusion, high energy physics and astrophysics are going to be intertwined. We need to study them both together. And there are a lot of exciting prospects for discovery in the near future. Yeah, that's a good question. So the question was, don't we already know that the expansion of the universe, the accelerating expansion is not constant because we had this early epoch of inflation where the expansion of the universe was accelerating, and then it stopped for a long time. We don't know what happened, but then it's accelerating again today. So it's a good question. The expansion of the accelerated expansion during inflation, we actually know the expansion rate was not constant because it ended. And we have some evidence from the data that not only are we here, so we know it ended, but there's actually some evidence of how that expansion rate changed with time in the data itself. And we know it wasn't constant. And that's one of the things that we try to measure. So we know there's more about inflation to measure. The dark energy today, the idea is that there's this low level amount of energy stuff, this cosmological constant, that was really small and just too small to have any effect until recently. So it's only once all the other matter dilutes sufficiently that constant term becomes important. And that's why, but it could be that from here on, the expansion of the universe just accelerates at a constant rate forever and is truly constant. So the question, it could be that it's truly constant, whereas inflation we know isn't truly constant because we have some evidence of that. But it is enormously interesting if to try to connect them, although I don't know of any great models that do connect those two epochs. So I mean very, very sensitive. So the South Pole ones will also make high resolution maps, but the South Pole is by far the best place to do these very sensitive maps of polarization sufficient to detect primordial gravitational waves. So they're looking for they're measuring delta T over T more accurately as opposed to higher resolution. Yeah. Oh, actually, I didn't mean to mention that. I meant the cosmological constant. Oh, sorry. The question was, I mentioned that there are searches for spatial variations in the cosmological constant, and the question is at what scale. So I'm being a little bit like, I'm being super oversimplifying here, but roughly speaking, people look for dynamical dark energy, which has perturbations on cosmological scales. David. So the question was, what sort of physics can you learn about if you measure the polarization of the CMB well? And you measure, you learn a number of things. The polarization can be generated by some of the same processes that generate the temperature fluctuations. A lot of the same processes that generate the temperature fluctuations will generate variations in the E mode polarization. And so we get a second map of everything. And we get better precision on things. So the polarization, one of the main things that we hope to learn is to have better constraints on these searches for new particles. So the forecast that I presented for the CMB S4 experiment on the energy density of radiation in the early universe is primarily coming from polarization and temperature together. One hopes polarization is a cleaner probe of gravitational lensing. So polarization will be probably the best way, we think now, to measure one of the best ways to measure the neutrino mass. And then there is this distinct process of primordial gravitational waves that generate the particular parity odd polarization modes. And that is the cleanest way to go after primordial gravitational waves and the energy scale of inflation. Yeah, that's a great question. If we could measure the cosmic neutrino background, what would we hope to learn? So there is an experiment that's trying to do this, and it's called Ptolemy. It's in Princeton, and it's on the 2030 time scale. And they still need neutrinos to be kind of massive compared to what we think their masses are from cosmic microwave background. And I think it would provide a new, these neutrinos were emitted so much earlier from the cosmic microwave background photons that it would be this really exciting additional like piece of putting together this thermal timeline of the universe. In terms of probing new physics, if we saw something that we didn't there's no guaranteed signal of something that we don't already know, but we would have the opportunity to see something that we didn't expect, for instance.